Hey guys.
Hey, Professor.
Hey, how's it going?
It's going.
Studying for the exam?
Yeah, I'm struggling on the homework.
Uh, well, I mean, do your best on the homework and the don't spend too much time because the I will post the solutions tonight after everyone turns it in. So, just put down what you got and and then make sure you leave time for studying as well.
Yeah, that's the problem. I don't have anything to put down yet.
Oh,
Yeah.
which one are you stuck on?
um, I was stuck on number 3.
3? Okay. Let me bring up
Yeah,
my
because I
textbook.
I honestly just don't know how to go about it. Because the table in the book, I'm getting like some crazy large shape factor, and it's not working out.
Okay. Let me see. Let me bring up my solutions for it. I think it's down here. Is this the formula? Hang on, let me write it down. So the formula for the shape factor that you should be getting is this one right here. Oops. So it should be S is equal to 2 pi d divided by 0.93 L1 divided by L2 minus 0.05. Is this the one that you're using for the shape
So
factor?
that's the formula I got, but it's ln of L1 over L2.
Oh, right, Ln. Yes, yes. And you said plugging this in is giving you a really large number?
Yeah, I'm getting like 212 or something like that.
212. Oh yeah, that's right. That's right. You should be
Okay.
getting that. Mhm.
Yeah, and whenever I plug it into my thermal circuit, it's I don't get that answer that's in the.
Let me let's see. It could be that I made a mistake in my work. Let me see. Thermal conductivity is 100.
Not the garage? Oh, I was. Oh, nice. I'm gonna do some laundry right now too.
Right. And so when you plug this in, or when you plug the shape factor in, like you should get a resistance value, which is 1 over SK, right?
Yep.
And K is 100.
Yep.
And so you should get 0 or 4.7 times 10 to the minus 5, right?
Yeah, that sounds about right.
Okay. And then we compute that together with the other resistances. So let's see. So there's two other ones, right? So there's the convection resistance for the interior and the convection resistance for the exterior, right?
Yeah.
So Rn should be 1 over Hi AI.
Yep.
When you plug that in, you should get 0.000833, correct?
Yeah, that sounds about right.
Okay. And then for Ro, let me just turn the page. And then Ro, you get 1 over HOAO. And then
Yep.
from this, you get 0.0023, correct?
Yeah.
Okay. And then you add up all the resistances. You get R total
Mm-hmm.
is equal to 0.00318.
Mm-hmm.
And then from there, just dividing, right? So then the temperature difference is 95 minus 25 divided by that. And then your Q, yep, should be 95 minus 25 divided by 0.00318. And then you should get a heat transfer rate of 22,012.3, right?
Yeah, I'll have to double check my math there because that's exactly how I did it.
Okay.
Yeah. Thank you, Professor.
Yep.
And then what if you could answer one more question? I'm just confused for part 5A,
Yep.
which formula you wanted us to start with.
Yeah. So
I'm
for that
just-
one, I want you to start with the full lump capacitance. So it should be the one with basically everything. So both all three convection, heat flux, and thermal generation to that. So it should be.
is that the general heat equation?
Yes. Yeah. General lump
Okay.
capacitance. So it's d theta dt plus HA over rho VC theta is equal to Q dot over rho C. Oops. No. Plus QS double prime A sub Q divided by rho VC. Yep. So
Okay.
that's general lump capacitance right there.
Okay. All right. Thank you, Professor.
Mm-hmm.
Hey, Professor,
Hey, how's it going?
how was your weekend?
Good, good. How's yours?
It was cool. I had a quick question on the homework.
Sure.
For question number 3, one of the parts asks for I think it was part B,
Mhm.
where we had to find like the total. Sorry. Mm, Yeah, for number 3, problem 3B, where it
Mhm.
asks for the outside temperature O.
Yep. Hmm.
How do we find that when the TI wasn't really given? It was just TI infinity or T infinity I. Do
Yeah,
we
yeah.
just use the same I or
No,
same?
what I mean by outer temperatures, I mean on the surface of the square pipe. And so like you have your square pipe that looks like this, right? And so we know the temperature on the inside, and we also with the temp, the temperature of the fluid on the inside and the temperature of the fluid outside. And so where I wanted you to solve for the temperature was right here. And so if you draw your thermal circuit, we have 3 resistors here, right?
Mhm.
I want you to solve for the temperature basically right here. Because this would be like our convection of the interior. This is our convection of the exterior. And then this middle resistor, this would be like the 2D resistance that you compute from the shape factor, right?
Oh, okay. And then for that top one, that was for A.
Yes, yeah. So this is the computations for A. Mhm.
So
Except for this one. This is for problem 5.
so then for that one, when we're talking about total heat loss, why aren't we using sorry, what is the resistance?
You mean this guy in the bottom here?
Yeah.
Yeah, so that's
Uh,
that's that's the total resistance of the entire circuit, because you have this circuit right here, right? So you have the internal convection, you have the external
uh,
convection, and the 2D. And so I just I computed all 3 resistances and I just added them up together.
wait. Oh, I guess I deleted it. All
Yeah.
right.
And so
I'll
I
try
think
it again.
the tricky one I think is the 2D resistance, and so for that you need the shape factor for that. And then once you have the shape factor, you multiply it by the thermal conductivity, and then you can compute that, and then you do 1 over that, and then that's the resistance of the 2D. Yeah.
For the shape factor, for the 2D one, um, since it's hollow, would you have to like do 2 shape factors and then like subtract?
Nope, you just need 1. So if you look into the table in the book, you should see this exact situation of like a hollow square channel. And so I
Oh,
think
okay.
the shape factor for that is like 2 pi d. I can literally just add it 0.93 ln of L2 over L1, or L1 over L2, whichever one's bigger, minus 0.05.
Okay.
Yeah. So this is from table 4.1.
Okay.
Yeah. Mhm.
Cool. Thank you.
Mhm.
Professor, will you be available after class today for questions?
Yep. Yep. I'll be here after class, so you can ask questions then. Mhm.
Okay, thank you.
Yep.
Professor, and then for the exam, we're allowed a note sheet, right?
For the exam, it's open notes, because
Oh.
it's I can't see you guys, so you can use any information that's available to you for the class. So you can use your textbook, your notes, you can use the lecture videos. The only thing that I ask is that you just don't talk to anyone in the class about it. It should just be your own work, and then you stick to just the materials in the class. So last semester there were a lot of issues of people posting exam questions on check, so I don't want to see any of that. But anything that's been posted for the class, the lecture notes, the videos, and your own personal notes, all of those are fine for the exam. Yeah.
Okay, and then the material today will not be on the exam, correct?
No, today we're starting something new. It's not going to be on the exam.
All right, cool. Just
Mhm.
double checking.
Yep. Okay, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing?
Pretty good. A lot of work this week, but
Good. Good. Yeah, I know I always feel a little bit insensitive asking that the day before an exam, because I know you guys probably are really stressed, but hopefully everyone was able to, get some studying done and at least rest a little bit this weekend. Okay. Okay.
Professors always do a really good job of making sure exams are always right back to back or on top of each other. So If there was a category for judging a department by this, our engineering department is definitely an A. So
I know that's a big issue too, and it's tough just because it's, you know, we usually faculty, we don't talk to each other about our exams, but usually, you know, just by the pace of what the class goes, like these weeks, you know, 6, 7, 8, this is kind of like the perfect time for the exams, just in terms of the amount of content that we cover. So it just ends up being like that. But yeah, it sucks, I know, but it's you know, it just kind of has to be like that. Okay. And so, you know, with that, you know, hopefully everyone knows that the exam is on Wednesday, right? So this is the only lecture that we're going to have this week, and Wednesday is going to be the exam, and it's going to take place just during the class period. So the exam is going to open up on Canvas starting at 2:30, and then it's going to end at 4 p.m. So I gave you an extra 15 minutes on the exam, so you can go up all the way up until 4 p.m. just because I know, you know, like scanning and uploading your answers takes some time. So I wanted to make sure you guys have some time to do that as well. Okay. And so I wrote the exam last week, and I took it, and, you know, I'm always hopeful that, you know, it doesn't take too long. And, you know, my own, you know, myself taking the exam, it only took me about 10 minutes. So hopefully, you know, for you guys, you guys will have enough time for the exam as well. Okay. And so just like I mentioned before the class today, you know, if I know if some people were still coming in, you know, it's an open book, open notes exam. You know, I'm not physically there with you in your room, because that would be really weird. And so, you know, you know, you can use any material that's been posted for the class. So that's, you know, the notes, the lecture videos, you know, your own personal notes, you know, anything, your textbook, you know, all of those are fair game. Okay. The only thing that I ask for the exam is that, you know, you just make sure that it's your own work. So no talking to anyone else during the class, in the class during the exam, no posting the exam questions on a website or anything like that. And getting help from that. So the exam should just be your own work, but any of the material that you have, you know, homework solutions, notes, lecture videos, your own personal notes, textbook, you know, feel free to use those, but, you know, don't seek outside help. That's kind of my only thing. Okay. Anything else I want to say about the exam? So the review video I posted on Friday. So I did notice that it's been viewed quite a bit. So hopefully that was helpful to everyone. So definitely take a look at that as well, because I you know, it did cover some good stuff for the exam, and then help you prepare for Wednesday. Okay. The third homework assignment, which, you know, the exam will cover that homework assignment, that's due tonight as well. And then as soon as everyone, basically, as soon as the deadline passes for that, I'm going to upload the solutions onto Canvas as well. And so you'll have that to help you study. I mean, I know homework 3 was a little bit long too. So, you know, I think hopefully the solutions will be helpful to you guys as well. Okay. All right. And so with that, you know, today we're going to start a new topic. And so this topic's not going to be on this exam, but it will be on the future ones. Okay. I think this is kind of a good thing to kind of start, you know, right before the exam, because it's mostly just conceptual information and no calculations yet. And so we'll kind of start those probably next week. Okay. All right. So are there any questions that I can answer either about the homework or the exam before we get started today?
Just to reiterate, if we have questions on the exams, will you be on Discord or
Yes.
do we do Zoom? Or?
Yeah. So I'll so during the exam period, I will be here on the Zoom call, so you can ask me questions. But you don't have to be here. You know, if you'd rather not open up Zoom at the same time, that's fine with me. But I'll be available on Discord, and I'll be available through emails. You know, for questions. So you know, you can send me your questions through that. Mm-hmm.
I also had a question. As far as like, do we need to write down the problems for the exam or go over any like formal guidelines about like actually writing it on a piece of paper?
Yeah, no, that's a good question. So the exam is split into kind of 2 sections. So the first section is all short answer questions, and so those you'll type directly into the browser. So I basically set up a quiz on Canvas so that you can type those out. So that'll save you at least some writing time for the short answer questions. And so there will be 3 of those. So there will be 3 short answer questions. And then the last 2 questions on the exam will be problem solving questions. And though for those ones, I will ask that you write your whole solution out on paper and then scan and upload those onto Canvas, just so I can see your work. And just like I always do, you know, for those problem solving questions, I grade, you know, 90% of the points on your work leading up to the final solution. And so, you know, if you do the whole process and you write down all the equations right, but you get the final solution wrong, you know, that's like 90% of the points for me, because, you know, I feel like in this class we're learning the process on how to solve these, and we're learning the concepts. So whether you punch it into your calculator or not is not, it's not as important to me. So that's why for those questions, it's really important that you really, you know, take the time and list out all the steps in your work, because that's how you get full credit on those questions.
Okay, real quick question. So I normally use like an iPad when I'm doing my homework.
Mhm.
Will that be acceptable, or do you want to like pen and paper type thing?
No, as long as you can show me all your work, you can even type it up in Microsoft Word if you want to. Although I think that's really time consuming. But anything that you can do to you know, basically show your process on how you got the solution, anything is fine with me.
Okay, thank you.
Yep. All right. Any other questions about the exam? All right. If you think of anything else, you know, definitely don't be afraid to send me an email or, you know, ask me at any time today, you know, because it's, you know, virtual exams, I think every faculty does it different. So definitely, you know, get your questions out just to kind of make sure that, you know, you kind of know what to expect. Okay. And so with that, let's go ahead and get started today. Okay. And so today we're starting a new topic. It doesn't seem like a new topic, but it's kind of almost a different perspective on something that we have been using. And so, you know, I call this unit the whole convection unit. Okay, so what we're starting today and what we'll finish up on next Monday is this first set of lecture notes called Introduction to Convection. Okay. And so at first this might seem kind of strange because we've been using convection all this time, right? And so basically anytime we have convection, you know, we've been using this this formula called, you know, Newton's law of cooling, right? And so what we've been saying is Q convection is equal to H T. Usually it's some surface temperature, so we'll call this TS minus T infinity, okay? And this is for a situation where, like, say we have a solid here, okay? And outside the solid we have some moving fluid. Okay. And this fluid is moving past. Usually we denote this by some arrows. And usually for this, we give it, you know, its convection coefficient H, and also its ambient temperature T infinity, okay? And then TS would be this surface temperature right here, okay? Okay, so we've been using this, and we use it in our circuits, right? So we have our convection thermal resistance, you know, and all of it seems good, right? So it seems like at this point we understand everything that we need to know about convection, okay? But in practice, it's actually not this simple, because, you know, if you've noticed, you know, one thing that we've been using is this parameter H, right? And what this H is, we've been calling this H the convection coefficient, right? And what that convection coefficient represents is it basically represents how strong the convection heat transfer is, right? And so the higher your value of H, then the more heat that the fluid can extract, right? And you know, the more efficient your heat transfer is. Okay? And so we've been using this value of this H parameter kind of, you know, without really thinking about it too much. But in practice, you know, this H is actually really difficult to determine. Because it's not something that you can just look up in a table. Like you can't just look up, you know, the convection coefficient for water, because that will, you know, you won't find anything for that, right? Because in reality, this H is almost like a dynamic variable. So it actually depends on a lot of different factors. Okay? Okay. And a lot of it has to do with actually the fluid mechanics of the flow that goes around it. Okay. And so some things that it depends on are like the velocity of the fluid flow. Right. It depends on the direction of the flow, or the flow patterns, or the flow field. Right. It depends on the thermal properties of the fluid itself. Okay. Because the fluid is, just like any other substance, has its own thermal conductivity, right? We don't use it often because most of the time, we consider fluid to be moving, and so we use the convection coefficient. But if you have like a still pool of water and the fluid's not moving, then you would use the convection or the thermal conductivity for that. And so the value of H, of course, depends on that. Okay? And then one more thing, that we'll talk a lot about, over the next few weeks, is what I like to call the nature of the flow. Right? Or in other words, whether the flow is laminar or turbulent. Okay. Okay. And if those, hopefully those terms, laminar and turbulent, ring a bell from 333 for you, but if not, it's okay. We're going to review it. And so, part of today is we're going to review some of the key concepts from fluid mechanics that have to go with this. Okay. Because this whole unit of convection right here is, from what you'll see, is that this is kind of where thermodynamics, heat transfer, and fluids kind of all converge into one. Okay. And so we're going to be drawing a lot on our knowledge from fluid mechanics, to develop a lot of the theory here. And you'll see kind of why fluid mechanics is a prereq for this class. Because up to this point, we haven't really used fluid mechanics at all. We've just kind of been studying heat transfer as its own thing. But you'll see that once we start really diving into convection and really starting to analyze it in detail, we're going to need a lot of knowledge from fluid mechanics to kind of help make this work. Okay. All right. And so, this is what we're going to be doing over the next few weeks. And then, this lecture and also the one on Monday is meant to just give you an introduction of, why computing H is so interesting and why, it's so difficult. Okay. All right. Any questions on any of this? Okay. All right. So let's dive right into it. And so the first thing, that we'll talk about from fluid mechanics is this concept of the boundary layer. Okay. Okay. And so, I know every fluids faculty kind of teaches differently, but at least I know for the sections that I teach, the boundary layer is something that we don't really get too much of a chance to talk about because it kind of happens near the very end of the course. And so, some of this might be review, but some of this might also be a lot of new information. So, I call it review, but if it's either, if it's all information, that's okay too. So we're going to build up kind of everything from scratch. Okay. Okay. And so the idea of the boundary layer comes from this, right? And so, a lot of times what you have in convection situations is you have a fluid that flows over a surface, right? So let's kind of draw that. Okay. And so let's say that we have a fin, right? And so let's say that we have a fin that looks like this, where we have the leading edge of our fin out here. But this could be, any other surface, but, it looks like a fin, so I call it that, right? And then on this fin, we're going to be blowing a fluid over it. And this fluid will have a velocity, we'll call it U infinity, okay? Okay. And just a little terminology, as we go forward, I'm going to use the term free stream a lot. And so what I mean by the free stream is that's the velocity of the fluid that's kind of far away from the surface. Okay. And so, if you kind of remember of, how we usually draw convection, we usually draw 3 arrows that are uniform like that. That's basically to indicate that the velocity is kind of uniform on the outside, far away from our surface, okay? And so when I say free stream velocity, what I mean is, there's usually just one velocity, and that's just the speed of the fluid somewhere far from the surface, okay? All right, and so as the fluid strikes this structure, you'll actually see this thing form on the surface. It's a very thin layer of fluid, and that's called the boundary layer, okay? And so the boundary layer usually looks something like this. Right? Right? And so it gets this name boundary layer because it's literally like a layer of fluid and that's right next to your solid boundary, okay? So that's kind of where it gets its name. One thing of interest inside the boundary layer is how thick it is at any given point. And so we usually give the symbol for the thickness as delta, okay? Okay. And the other thing that's of interest inside the boundary layer is how the velocity changes within the boundary layer, okay? Or in other words, what the velocity profile looks like. And so the velocity profile usually looks something like this. Okay. So it almost has this almost like a parabolic form, right? And so every boundary layer kind of looks like this to some degree. So at the surface, basically the surface isn't moving, right? So any fluid that directly contacts the surface has to be at 0 velocity, okay? And so the way we usually call that is that the fluid that touched the surface is not going to slip. So we call this the no slip condition here. Okay. And then as the fluid gets away from the boundary layer, the fluid particles are going to start to speed up. Okay. Eventually, until it reaches the edge of the boundary layer, where outside the boundary layer, the fluid velocity is going to be u infinity. Okay. And so at the very top of the boundary layer, you can think of the fluid velocity as u infinity. Okay. And then everywhere in between, if you kind of think of at the surface, we have 0 velocity, and at the top of the boundary layer, we have u infinity. Everywhere in between, we call that the velocity profile. Okay. Okay. All right, so that's kind of intuitively what the boundary layer is. A lot of times you don't really see it, and so like if you look at kind of the air that flows past an airplane wing, it's really hard to see the boundary layer unless you zoom really, really close. You kind of squint your eyes really carefully because a lot of times it's really, really thin. Okay, but the whole purpose of the boundary layer is to make sure that there's kind of this transition, right? Or in other words, a smooth transition between our two extremes here, okay? And our extremes are the different values of velocity that we have going on, okay? Because at the surface, for the fluid that's contacting the surface, we have 0 velocity there. Okay. And then at the edge of the boundary layer, we have our free stream velocity. Okay. Because the fluid can't just make a sudden jump, right? So it can't just go from 0, then all of a sudden it's going to u infinity, right? There has to be some kind of transition zone in between. And that's exactly what the boundary layer does, okay? And then, and so throughout the boundary layer, you have, as you go farther away from the surface, you see fluid particles that get successively faster, okay? All right, any questions on this? Okay. All right, so let's talk about, why this, why we have this smooth transition to begin with, or what's the physical mechanism that causes this transition to be smooth. Okay, and that physical mechanism here is viscosity. Okay. And so viscosity, probably you've heard about it a lot in your fluid mechanics class, but intuitively remember viscosity kind of acts almost like it acts almost like friction for fluids. Okay. Oh, question? Is that distributing? Oh, it's distributions. Sorry.
Sorry, it's just kind of hard to read.
Yeah. And so the analogy that I always give to my fluid mechanics classes when you think of viscosity is, when you rub your hands together, not right now because my hands are really sweaty, usually you generate heat, right? Because as you slide your hands together, right, there's friction forces that are kind of impeding the motion, and then and that's basically what friction is, right? And so viscosity or viscous forces basically apply the same effect for fluids. Okay. And so basically intuitively what you can think of is this, like, so you have your solid surface here, you have your fluid particles that are flowing past, but because of viscosity, the surface is applying almost like a friction force, a retarding force to the fluid right next to it. Okay. And so what that's going to do is going to slow the fluid particles down. Okay. And then those fluid particles are going to place a friction force on the next layer of fluid particles, right? And it's going to slow it down. Okay. And this is going to keep going until you reach the edge of the boundary layer, right? And so that's why you have this kind of smooth transition strictly because of this friction force, right? Because that friction force, it doesn't completely stop the fluid, right? And so it's just like with friction, right? So with friction, you can keep rubbing your hands together. It might get a little bit harder, but you can still rub it, but it's going to slow you down a little bit, right? And so that's basically what viscosity does. Okay.
Like the rocks that get smooth in the waterbed.
Yep, exactly. Yep. Mm-hmm. Yeah, it's a great, great analogy there. Mm-hmm. Okay, and so let's talk about delta a little bit, because that's usually one of the primary, variables of interest in a boundary layer. And so we usually give this symbol delta, okay? And if you actually look in your fluid mechanics textbooks, there's lots of different definitions for delta. There's lots of different ways people can characterize the thickness of the boundary layer, because it's not like there's a distinct line in your fluid, right? And so like if you look at flow past an airplane wing, you don't see like a little line as you look outside the airplane, like that's the boundary layer. And so you can't really see it. And so the way people define it can be kind of different, but for the sake of this class, I'm going to stick to just kind of the simplest definition. And so the definition that we'll stick to in this class is this is the location where the velocity basically returns to this free stream velocity. Right? And so by location, I basically mean distance from the surface. Okay. And so to write a formula for it looks like this. So we have U of delta, okay, is equal to 0.99 u infinity. Right. And so that 0.99 is there basically just to say that, you know, once we reach about 99% of our free stream velocity, then we're basically at the edge of the boundary layer. Okay. And of course, you know, this 0.99 is arbitrary. So, you know, there's no, you know, it's not like, you know, Navier-Stokes said that, you know, you have to use 99% because that's, you know, that's just kind of for ease of visualization. Okay. But this could easily be like 95%, 99.99%. So that exact number is arbitrary. But, you know, what I want you guys to kind of take away from this is once the, you know, the fluid velocity grows and it gets pretty close to the free stream velocity, then that's what we define as the thickness. Okay. Okay. And so, you know, now that we've established what the boundary layer is, let's talk about, you know, the differences between the boundary layer, which is, you know, which I'll define to be one region, and the other region, which I define as the free stream. Okay. All right, so let me draw our surface again. Okay. And then I'll draw the boundary layer on top of this. Okay. And remember, this is occurring because we have fluid that's flowing this way. Okay. And so the two regions that we'll talk about, and, you know, and we'll focus just on the boundary layer region, are these two. So inside the boundary layer, we call this the boundary layer region. Okay. And then outside the boundary layer, we have the free stream region. And each of these regions have certain characteristics, you know, that we'll talk about on the next page. But I at least wanted to, you know, at least visually establish what the two regions were. Okay. All right. Any questions on this so far? Okay. Okay. So let's characterize these two regions in terms of two quantities, right? And so the first quantity that we'll talk about is velocity gradients, and the other one is the amount of shear stresses. Okay. Okay, so let me make two columns here. So on one side, I'll have the free stream. Okay. And on the other side, we have the boundary layer. Okay. All right. And so in the free stream, generally what you see is that the velocity is uniform. Okay. Okay. And so all that means is basically the velocity is basically the same everywhere outside the boundary layer. So, you know, the direction is the same and the magnitude is the same. And so this has kind of two important consequences in terms of the equations that we'll talk about. Right? And so the first thing is that the velocity gradients are very low. Okay. And that makes sense because a gradient is basically describes a change in something. And if the velocity is uniform everywhere, then it's not really changing all that much. Okay? And so basically, you know, we can say our velocity gradients are very low, right? And then mathematically, the way that we describe gradients is with derivatives, right? Okay. And so if we take the derivative of the velocity, say in the y direction, right? So du dy, we can basically say that this is very low. Okay. And then if the velocity gradients are very low outside the boundary layer, then this also means the shear stresses are very low. Okay. Okay. Shear stresses are nothing more than the friction forces that I was talking about earlier. Okay. Because in order to have viscous friction forces within a fluid, you basically need to have differences in velocity. Okay. But since we know that the velocity gradients or the velocity differences are very low, then, you know, we're going to have very low shear stresses as well. Okay. Okay. And so that's in contrast to the boundary layer region, where inside the boundary layer, we know the velocity is rapidly changing. Okay. And that's, that's just like what we were talking about before, because in the boundary layer, the fluid velocity has to go from 0 at the surface up to the free stream velocity. Okay. And so in order to do that, it has to make a lot of changes and it has to happen really quickly. Okay. And if the fluid is changing rapidly, this tells us that the velocity gradients are very high. Okay. Right. And so if we take the derivative of the velocity inside the boundary layer, and so we say du dy, okay, this is very high. Okay. Right. And then if the velocity gradients are very high, then this also means that the shear stresses are very high as well. And so when we talk about the differences between the free stream and the boundary layer regions, I want you to think about these two things, okay? First of all, think about the velocity gradients, or how rapidly the velocity is changing or not, and then how that correlates to the shear stress, okay? Right. And then just to kind of remind you, if you have the velocity gradient, you have du dy, then we can actually compute the shear stresses or the viscous friction forces with this formula, okay? And so we usually give this a symbol tau, and it's going to be equal to mu, which is the viscosity, times the velocity gradient. And so this tau s here is the shear stresses. Okay. Viscous shear stresses. Okay. This mu right here, this is viscosity. Okay. And we've already defined du dy above, which is just simply the velocity gradient. Okay. Okay. All right. And so, we've already talked about, what this shear stress is doing, right? And so, this shear stress is basically being applied on every layer of fluid inside the boundary layer, right? And that's what basically causes the velocity gradient, or the velocity profile to look like what it does, okay? Another way that you can interpret the shear stress is that it kind of acts as like a vehicle to transfer the momentum of the surface to the fluids, okay? And I'll explain that more on the next page. But before I turn the page, are there any questions on this?
Well, never mind. There's a sort of tangent.
Mm-hmm.
Is it all right if I ask you?
Wait, say again?
Is it all right if I ask you a sort of tangent question?
Yeah, go for it.
Is that what they use for the hose attachment, like the those power wash hose attachments?
Oh, I think that's a little bit something different. So the that's definitely a lot more of a fluids question. I would need to look into it more before I answer that question
Sorry
in case
about
there's anything wrong. But no, it's okay. Yeah, it's a good question. Now I'm curious myself. I'm going to look it up afterwards. All right. Any questions on this? Okay. Okay. And so, the reason I bring up the shear stress is that this is kind of the vehicle through which momentum is transferred. Right? Okay. And so what do I mean by that? So what do I mean by transferring momentum? which seems kind of strange because the surface in our case is completely still. And so, that means our surface doesn't have any momentum. And you would be right. And that's exactly what's being transferred, right? And so the zero momentum of the surface is being transferred through the fluid through the shear stress. Okay. And so visually, it looks something like this, right? So let me draw our surface again. Okay. And so there's our boundary layer, right? And so the surface we know has no momentum because it's still. Okay. Whereas in the free stream, the fluid's going at a velocity u infinity. And so outside the boundary layer, the fluid has a lot of momentum. Okay. And so what the shear stress is basically doing is it's basically saying that, since the surface here has no momentum, it's basically propagating that through the fluid. Okay. Right. And then the net result for that is that smooth velocity distribution that we showed before. Okay. And so think of it, like this, think of it as you go layer by layer of the fluid as you go up to the top of the boundary layer, right? And so at the very bottom layer, you have your surface and that has no momentum, right? And so on the very next layer, right, that surface, because it's not moving, is imparting a friction force on the fluid particles right above it, right? And so what that's doing is basically kind of pulling those fluid particles back so that they don't move as much, right? And so what results is you have kind of this tiny arrow here right next to the surface because those fluid particles are being kind of held back by the shear force that the surface is generating, okay? And then what's going to happen is that those fluid particles from that arrow are going to impart the shear stress on the next layer, right? Thus causing it to move, thus causing them to slow down, but not nearly as much because they're moving a little bit faster, okay? And then as you progress up the layers, the shear stress is making an effect, but that effect is kind of less and less until we reach the edge of the boundary layer. Okay. Okay. And then kind of the parameter that kind of modulates this whole thing is our viscosity, right? So remember we had tau s is equal to viscosity du dy. Okay. Okay. And so depending on the viscosity of our fluid, that's going to change the magnitude of our shear stress. Okay. Okay. In other words, what we can say is that viscosity will modulate the amount of shear stress that's experienced in the fluid. Okay. And so, what that's basically saying is if you have a fluid that's more viscous, so say like you have, a jar of honey or molasses or something like that, right? Because those are very viscous fluids, then what you can say is that those fluids transfer momentum really, really easily throughout throughout them, right? And so that's why it's really hard to kind of pour out a jar of honey, right? Because honey is so viscous. Because what's happening when you're trying to pour out that jar of honey is that, because the jar itself isn't moving, right? So you're kind of keeping it still like this, the zero momentum of the jar walls are propagating through the fluid really, really easily. And so that basically causes the honey to move very slowly because momentum travels so well. You compare that to something like water, where water is not nearly as viscous, right? And so if I pour this glass of water out into my laptop, first of all, the lecture would probably be over then. But it moves so easily because, even though the glass itself doesn't have any momentum, that zero momentum doesn't travel through the water as much because the water is just not very viscous. Okay. And so, after this, we're going to transition to thermal boundary layers, but I want you to kind of hang on to this kind of interpretation of viscosity, because we're going to make a parallel analogy with thermal. Okay. All right, any questions on this? Okay. Okay, so now let's talk about thermal boundary layers. So like what we've talked about so far is just, you know, fluid velocity boundary layers, but thermal also has its own boundary layer as well. Okay, and so we can draw a similar situation for this. Okay, and so we have our surface here. Okay, we have a fluid that's flowing, and so we have, you know, our arrows like this. But since we're talking about thermal boundary layers now, we're not going to be talking about the velocity, but now we're going to be talking about the temperature of the fluid. All right, and we always give that the symbol T infinity. Okay. And then meanwhile, on the surface right here, you know, we have our solid surface, and this is at some different temperature. And so we'll call this TS, or temperature of the surface, right? And most of the time, you know, as we typically see in our heat transfer problems, there's a difference between TS and T infinity, right? So TS and T infinity usually are not the same. Okay, and so what develops from this is a boundary layer, just like in the velocity case, right? And so we have a region that looks like this, okay? And then inside the boundary layer, we have, you know, something that basically looks the same as before, right? Because in the velocity boundary layer, you know, the velocity boundary layer, the purpose of that was to transition between the condition at the solid surface and the condition in the free stream. You know, for thermal, it's exactly the same way. Right? And so inside the thermal boundary layer, we have a transition zone between the temperature at the surface and a temperature of the free stream. Okay. And so it might look something like this. Where at the bottom of this graph, we have TS, right? And so basically the fluid that's right next to the plate will have the same temperature as the surface. And then as you get outside the boundary layer, you know, the fluid will have the same temperature as the free stream, okay? And then in between that, we have our boundary layer, which is, you know, where the transition particle or the transition occurs, okay? Okay. And so, you know, the mechanism through which, you know, this thermal boundary layer develops, and, you know, the way that this temperature distribution develops is, you know, almost exactly the same as in fluids, okay? Except now, you know, we're talking about thermal stuff instead of fluid mechanics stuff, right? Okay. And so physically what's happening is that, you know, the particles that are in the boundary layer, you know, I want you to think of it kind of layer by layer, just like in the fluid case. Each layer is going to be transferring energy in between each other. Okay. Okay. Right. And then the way it does this, and the way it transfers you know, energy, basically we're talking about, you know, fluid particles to fluid particles that are right next to each other, right? The mechanism for this heat transfer is actually conduction. Okay? Okay. Because remember what conduction is. So conduction, remember, is the transfer of energy or the heat transfer within a stationary medium. Okay. So even though I know we have a moving fluid here, right? So we have a moving fluid that's on top, but if we look at kind of just a microscopic layer, right? And so if you look at just kind of this layer of fluid particles right here, right? Right. What you have are two layers of particles, you know, basically that look like this. Okay. Where to them, you know, maybe macroscopically, they might all be moving, you know, at a certain velocity, but to them, it might seem like they're kind of still, together with each other, right? Okay. And so relatively speaking, if you look at kind of two layers of particles, within a fluid, relative to each other, they're not really moving all that much. And so, within this kind of tiny band right here, basically between layers and layer to layer, the mode of heat transfer that occurs there is actually conduction. Okay. And then since we basically have conduction in these tiny layers, we can characterize that using Fourier's law. Okay. And so Fourier's law looks like this. So I'm going to do the heat flux version of this. And so I'm going to divide it both sides by A. Okay. Right. And so what we have is a QF double prime is equal to minus KF times dt dy. Okay. And so that's simply just our Fourier's law. Okay. All right. And so the key parameter here is obviously KF, and this KF, remember, this is the thermal conductivity of the fluid. Okay. Or in other words, how effectively do adjacent particles within the fluid transfer energy to each other? Okay. Okay. Any questions on any of this so far? All right. Okay. And so in other words, what you can basically say from this Fourier's law expression is that, the amount of heat transfer or the amount of heat flux that occurs in the boundary layer is modulated by this thermal conductivity, right? And so, hopefully that should be ringing bells from like 10 minutes ago, because this is very similar to what we were talking about, with the viscosity. Okay. All right. So actually, let me write out both expressions here on the next page, and I'll kind of show you what I mean. Okay. All right. So on the one side, we're going to have the fluid mechanics, okay? And on the other side, we're going to have the thermal. And so for fluid mechanics, remember we were talking about the shear stress, right? And so the shear stress was given by mu F, or there's just mu, right? So mu was the viscosity of our fluid. And then we're going to multiply that by the velocity gradient, okay? And then for thermal, we had the heat flux, which is Kf minus Kf times the temperature gradient, okay? And what did we say about the viscosity here in this fluid mechanics situation, right? The viscosity basically modulated how well momentum transferred between each layer of fluid particles. Okay. Whereas on the thermal side, we have, instead of viscosity, what we have is the thermal conductivity, right? And this modulates how well heat transfers between successive layers of fluid particles. Okay. And so you can see, you know, kind of once we draw them side by side and we kind of draw the rules for those kind of things, we can see that, you know, they kind of play the same role, right? And so viscosity plays a role in the fluid boundary layer, right? And how well momentum transfers in that, whereas the thermal conductivity plays a much bigger role in the thermal boundary layer and how well energy transfers for that, okay? And so, you know, this is kind of a key point that, you know, I want you guys to remember, which is kind of the connection between these two guys, okay? Because they play very, very similar roles in terms of the, you know, in terms of how they affect the formation of the boundary layers. Okay. Okay. All right. And so with that said, you know, even though I drew both the thermal and the velocity boundary layers, you know, the complicated things that these two things often don't they don't meet up or they don't overlap each other. Often you'll have one that will grow faster than the other one, and so you'll have kind of, you know, these kind of weird things that happen, right? And so just to kind of show you, you know, let's say that we have a situation where we have a fluid that's not very viscous, and so, you know, the viscosity is fairly low, but the thermal conductivity is very high, okay? And so in that situation, you might have a fluid boundary layer that looks like this. You might have a fluid boundary layer that's very thin, okay? But then the thermal boundary layer might grow, you know, much more quickly than that, okay? Right? And so you have two kind of boundary layers going on, and they don't necessarily coincide with each other, okay? And so when this happens, you know, you have you know, several different regions here. So you have, first of all, the region next to the surface, where you're inside both the thermal and the velocity boundary layer, right? Then if you go outside of that, you have a region where you're inside just the thermal boundary layer. And then you go outside of that, then you have the free stream, okay? And then it starts to get extremely complicated because, you know, whether you're in one region or the other, or not in the region or the other, you know, that's going to affect, you know, how you compute certain things. So, you know, very quickly, you know, with the boundary layer stuff, it gets really, really complicated. And, you know, with the amount of fluid mechanics that I'm sure a lot of you have, you know, we don't really dive that much into boundary layers inside the fluid mechanics class because it's you know, quite honestly, you know, it's kind of a graduate level topic to really, you know, analyze a boundary layer and, you know, talk about, you know, how exactly does the velocity change, because it's very complex, right? And so, you know, we're not gonna be going into very, very heavy detail into, you know, into the boundary layers because, you know, like I said, that's more of a graduate topic. But I at least wanted you guys to get kind of have a conceptual understanding of what's going on, and, you know, and just kind of what the idea of a boundary layer is. Okay, any questions on this? Okay, right. So now let's talk. Let's kind of bring it back and let's talk about our convection coefficient, which is kind of, you know, the motivation for wanting to study this whole thing. Because all that boundary layer stuff, you know, all that's great. But for this class, you know, honestly, you know, if we can avoid that stuff, then that'd be great because it's really complicated. Okay, because what we're interested in is purely just H. Okay. Okay. Because if we have H, then what we can do is we can basically plug it into all the methods that we have before. So we can use either the heat equation, we can use thermal circuits, right? If we have H, that kind of unlocks a lot of stuff for us. But the problem is in a lot of practical situations is we don't know what H is, okay? But all this stuff on the boundary layer stuff will basically help inform us of at least, you know, what are the things that affect H. Okay. All right, so let's recall Newton's law of cooling. Okay, so remember Newton's law of cooling basically says that the convection heat transfer is equal to H times Ts minus T infinity, right? And so pretty simple, okay? But also, through this boundary layer stuff, we have another expression for the convection heat transfer, and that's given by our Fourier's law. Okay. Okay. And so inside our thermal boundary layer, we also know that Q convection is equal to minus Kf dt dy, okay? And then evaluate this at y is equal to 0, okay? And so this right here is heat transfer in boundary layer. Okay. Right. So if we set these two things equal to each other, because they both equal Q convection, then what we can do is we can come up with an expression for H here. Okay. It's not a very helpful expression, but it's at least an expression, right? And what we can do is we can draw some more qualitative conceptual conclusions from it. Okay. And so what I'm going to do is I'm just going to say that, since both of these equal Q convection, I'm just going to set them equal to each other, and then I'm going to solve for H. All right. And so what we have on one side, we have H times Ts minus T infinity. Okay. And this is equal to minus Kf dt dy at y is equal to 0. Okay. And if we divide both sides by Ts minus T infinity, what we get is H is equal to minus Kf dt dy at y is equal to 0, okay, divided by Ts minus T infinity. Okay. And so basically what we have is this formula here. We won't actually be using this formula to compute H, because dt dy it normally is very difficult to obtain within the boundary layer, but it at least gives us some idea of what this H actually depends on, right? Because up to this point we've just been using H, and we haven't really talked about what really affects H, or what really determines H's value. Okay. And now with this, we kind of have a first step on how we can actually determine, or what factors at least determine what this H is. Okay. All right, any questions on this? Okay. And so in particular, I want to highlight kind of two aspects of the previous equation. Okay. Okay. And so these are things that H depends on. Okay. And so in the numerator of our previous expression, the first thing that we see is Kf. Okay. And so Kf, remember, this is the thermal conductivity of our fluid. Okay. And the fact that it's in the numerator of our expression basically says that the higher our thermal conductivity, the higher H is going to be. Okay. And intuitively, this makes sense, right? And so if you have a fluid where the particles are really good at transferring heat to each other, right, then that's going to make it so that overall the convection coefficient should also be really high, because just the fluid itself is already just naturally really good at transferring heat. Okay. And so if you have something like a liquid metal, like a liquid mercury or something like that, then that's naturally, no matter how slowly that you flow it, it's always going to have a high value of H, just because the thermal conductivity of liquid mercury is really high, because it's basically a liquid, liquid metal. Okay. Okay. And so the other thing that it depends on is dt dy evaluated at y is equal to 0. And what this is the temperature gradient evaluated at the wall. And so basically what this tells you is that the quicker, the higher the gradient, then, the higher H is going to be, okay? And remember, gradient is nothing more than a change, right? So basically, if the temperature is changing rapidly within the boundary layer, then this is going to, make H bigger. Okay. And so from that expression, we've at least established two things about H, right? So we've established that if the fluid itself is good at transferring heat without any velocity, then that's good for H. Okay. And we also established that H also depends on this temperature gradient of the wall. So in other words, it depends on the nature of the boundary layer. Okay. And so it's a start at least, right? And so at least KF here is relatively cut and dry. But this guy, this is still really hard to compute because, stuff inside the boundary layer is tough. But at least we've established that, H depends on what's happening inside the boundary layer. Okay. Okay. And so now that we've, at least taken our first steps in understanding H, now it's kind of useful to kind of take a step back and kind of look at what we have here. Okay. And so let's take a step back and kind of remind ourselves of what we define convection to be. Up to this point, the definition for convection that we've been using is, heat transfer to a moving fluid. And because of the fluid motion, we often end up with enhanced heat transfer compared to just pure conduction, okay? And so that's kind of what we mean when we talk about convection. And so if we kind of break this up, so now that we kind of know everything that we know about the boundary layer and, and H, we can kind of break this up into two kind of, things happening at the same time, okay? Because what we mean by heat transfer to a moving fluid, we mean kind of these two things happening at the same time, right? And so the first thing that occurs is that, we have heat transfer through conduction from the surface to the fluid. Okay. Oh, that's the arrow. Okay. And so we saw that in the boundary layer. And so, we know that inside the boundary layer, we have basically conduction heat transfer, at least between the layers of the different particles. Okay. And then the other thing that comprises convection is a bulk motion of the fluid via the fluid flow. Okay. And so, when we say convection, we basically mean these two things happening at the same time. Okay. Right. And so, in fact, the fact that, this is kind of what convection actually is, some people out there actually claim that there is no such thing as convection, right? So I think I might have said something like this at the beginning of the class, right? They said convection is just kind of a made up term because there's no such thing, because what you have instead is basically just conduction, and then you have fluid motion that kind of sweeps it away. Okay. And so this is kind of intuitively what I think of convection. So in convection, you have a moving fluid, right? And so as the fluid comes past, the surface is going to release some of its heat into the fluid, right? And then as the fluid next to the surface either heats up or cools down, instead of staying stagnant right there, the fluid flow is going to sweep it away and go somewhere else, right? And so you bring kind of fresh fluid into right next to the surface, where the surface is going to release some of its heat. It gets swept away. A new set of fluid particles come in. It gets, and that ends up being more efficient than just having just a still fluid right on top, right? Because if you have just still fluid right on top, is that the surface will heat up the fluid right next to it, right? And then as the fluid particles right next to the surface get hotter, then that will impede future heat transfer, right? Because remember, heat transfer ultimately is driven by a difference in temperature, right? And so if you heat up the fluid right next to the surface, right, your temperature difference isn't as high, and that's going to impede some heat transfer, right? But if you sweep that fluid away and you carry it off with the moving fluid, then you have fresh fluid that's always kind of coming in, and so you always kind of maximize your amount of heat transfer from that. Okay. And
I have
so,
a question about that.
oh yeah.
So say you have a block that's constantly heating up, just an example, and it's in a case full of water, but that water is moving, it's sloshing around in that container, but it's not constantly going out and coming in, right? Would that be considered conduction then, because it's the same amount of water, but it's just moving around in a finite area?
No, it would still be convection, because that
Okay.
heat doesn't propagate all the way throughout the fluid. And so kind of a good example of this is like if you boil a pot of water, right? And so if you boil a pot of water, it's kind of the same thing. What you can do is you can kind of stir the water, and what that will do is generally, when you boil a pot of water, generally the water near the surface is not as hot as the one that's near the bottom, because the one that's near the bottom is near the heat source. But if you kind of slosh it around, then you bring basically the fluid that's near the top towards the bottom, and then that's going to heat that up. But then that hot fluid is going to come up right there. And so I think you're right that it's not going to be as efficient, whereas if you're kind of bringing fresh fluid all the way there, but you do get some convection effects, because you are kind of bringing fluid that's not as hot as it was before back in contact with the hot surface. And so from there, you kind of make it more efficient. And so if you're boiling a pot of water, you want the whole thing to boil, that's why, recipes will tell you to stir it occasionally, because that enhances convection heat transfer. So you bring kind of more fresh fluid down in there. And so it kind of heats, more efficiently throughout. All right. Okay, let's see. Okay. So any other questions on this?
Would that sort of apply to superconductors, or is that getting more into electricity and all that?
Yeah, so that's I think that's getting more into electricity and also more into material science, because I think in superconductors you actually play with kind of the material itself to try to enhance its conductivity, but I don't think you specifically have fluid flow in superconductors.
Okay.
Although I will say that my knowledge of superconductors is very, very small, so I could be very wrong about that too. But my impression has always been that it's more of a material science thing than a fluids thing. Yeah. Okay. All right. And so that's kind of the bulk of what I wanted to cover today. But we do have some more, a little bit more time. So I think maybe I'll save the rest of it for next time, because we do have a midterm exam the next week, and so I think I'll stop it a little bit early today. And if you wanted to ask any questions about the homeworks, about the exams, I think now would be a good time. But if you don't have any questions, then that's it for today. And then the next time we meet will be for the exam. So remember, you can come onto the Zoom call if you want to ask questions there, but you don't have to. I'll be available via Discord and email as well. So best of luck studying, everyone. Don't be afraid to reach out for questions. So I'll be available as much as I can over the next 3 days, to try to help you out with stuff, with any of that. Okay. So have a great day, and I'll see you on Wednesday if you come to the Zoom call. But if not, I'll see you next Monday.
All right. Thank you, Professor.
Thanks, guys.
Hey, Professor.
Yep.
Would you, by any chance, be available within like 30 minutes or so?
30 minutes? Yep, I should be.
Okay. Would I use the same Zoom access or use a different one?
Go ahead. Let's use the Zoom link for Monday office hours. So if you go to the Canvas page and then you click the link for Monday office hours, let's use that one.
Okay. All right. Thank you very much.
Yep.
Okay. All right. Bye.
All right. Bye.
Question for the hose attachment. I was talking about earlier. Would it be, would you want, I guess, like a laminar flow? Because like turbulent means like it's chaotic and it'll go unpredictable, right?
Yeah, so in terms of analysis and figuring out what's going on, a laminar flow would be preferred. But I think just naturally for those kinds of devices where you're basically trying to speed up the flow as much as possible, you're going to end up with turbulent flow because as soon as the velocity usually reaches over a certain threshold and the Reynolds number gets too high, then you end up with turbulent flow. So
Okay.
yeah.
And those water mills that use water as a like an actual saw blade, it comes from like where they're shoving as much, they're using as much speed converting into pressure.
Yep.
Okay.
Yes. Yeah. So you're talking like a water jet cutter, right?
Yeah. And
Yeah.
they
Yeah.
want it as small as possible because they want the smallest stream as possible to kind of continuously pound it over and over and over again.
Exactly. Right. Yeah. So
Okay.
they're relying on extremely high velocities there to basically create because whenever a fluid stream hits a surface, you create what's called a stagnation point. And so they're kind of relying on having very fast flow and making that stagnation pressure extremely high, and that's what ends up cutting. I think they also insert some kind of particulates, like I think it's like sand or something, into the stream to kind of enhance its kind of the cutting properties of the fluid.
Okay. Thank you. I had that when you were talking. I figure it would be better to ask later on.
Oh yeah. No, it's super interesting. Actually, I know that the department purchased a water jet cutter recently too, and Dr. Myral was the one that's kind of spearheading that. So if you want to learn more about that, I think he would love to talk about that stuff.
I have him for 306B, so I can
Nice.
ask him about that.
Oh yeah, ask him. I'm sure he would love to talk about it.
All right. Thank you, Professor. Have a nice day.
Thanks, you too. Did you guys have any more questions? Oh.
Yes, sir.
Yep. What's
I
up?
just have a quick question in the homework.
Sure.
I was just confused on how to go by number 2, like the design process.
Design process. Okay. Yeah.
Designing a better.
Sure. Yeah. So number 2, basically, you're starting out with a cylindrical fin, right? So the fin basically looks like this. And so in the first part of the problem, I basically had you assess, how well this fin is, right? So I asked you to compute temperature distribution, the heat loss, and the effectiveness. And so to design a better fin, what I'm telling you is that basically this circular cross section is not very good because it's it's basically a round thing. So what I'm asking you to do is basically to design, a cross-section shape that's more efficient than a circle, right? Because if you remember from our lecture notes on fins, right, we had this metric called the effectiveness, and I think it was like K over H times P over A, something like that, right? Yes, okay. And so basically we want to maximize this as much as possible, right? And so in particular, I want you guys to pay attention to this quantity right here, right? And so this quantity right here is the perimeter divided by the cross-sectional area. And so it's you can almost think of it like a ratio, right? So you have a ratio of perimeter and cross-sectional area. And so what this tells you basically is that, because, the effectiveness is like this, if you increase this ratio, so you basically change the shape such that you have a higher perimeter relative to the cross-sectional area, that's going to lead to a more effective fin, right? Because right now with the circle, the perimeter is basically given by 2 pi r, and the area is pi r squared, okay? And so you take the ratio between these guys, and then what you get is 2 over r, right? And so that's not very good because it's, a circle just naturally doesn't have a very high, it has more area than it does perimeter. And so what we said in the lecture is that to basically maximize this, this ratio here, you want to pick cross sections that are very thin. So instead of a circle, which is kind of, symmetric all the way around, if you kind of smush the fin where you kind of, make it smaller like this, then that will lead to a more effective fin. So what most people usually pick for this one is they pick a thin rectangle. Okay. And so they pick a cross section that looks like this, right? And then from here you're subject to design constraints, and so the design constraints said that no length in your design can be greater than 80 centimeters. Okay, and so the maximum length here of your design, this has to be 80 centimeters right here. Okay, and so now that you have this thinner cross section, then I basically want you to redo all the analysis that you did for the circular one. So compute the temperature distribution, compute the heat loss, and then compute the effectiveness. And what you should see is that simply by changing the shape of your fin, you're going to create a more effective fin. Does that make a bit more sense?
Yes, sir.
Okay, great.
Much more. Because I was confused, like, which one should I pick? Like, I looked at table 4.1. I was like, should I pick this one? Should I pick that one?
Oh yeah. So
I'm just going to, I was just trying over and over, but like, I was just like blindly trying, not knowing like, what am I supposed to do, or not knowing the goal.
I see.
The question.
I see. Yeah, for this one, you don't need table 4.1. So this is strictly just fin stuff. So it's just, you're just playing with the geometry. And so the goal is just to make something that's thinner. So you could even do like an oval cross section. I think someone tried that once, but generally just because it's simpler, people usually do like a thin rectangle, because that's then you can compute the area and the perimeter pretty easily from that.
I see. Thank you.
Yep. Mm-hmm. Was that your only question?
Yes, sir. That's pretty much it. And for the, actually, I have one more question, if you don't mind.
Mm-hmm. Yep.
So for the exam, like, do we have to like derive like our formulas, as in like show where this equation comes from, as in like like the derivations we do in class?
No. So on the exam, it'll be just like the homeworks basically. So you're just going to be using the formulas. So the only thing I ask is that when you use a formula, at least write down the formula that you're going to use, just so that I can follow your work. But you don't need to derive anything at all.
I see. Like, for example, like for this question, like we didn't have to like use the derivation, but we just used the formula given.
Exactly. Right.
So we just like use that formula and like write like a side note or something.
Yeah. So you can basically say that you're going to use the formula for fin effectiveness. Okay. And then you can just point to this formula right here, and I'll know what you're talking about. So you don't have to derive this formula at all. So just say that I'm going to use this formula. And then after that, you can plug in numbers for it, and then you can kind of continue the problem from there. But
I see.
Yeah.
Like for part A, because like I just used the formula given in the lecture notes.
For part A. Okay. So that's a slightly different thing, because those are particular. If you're solving for the temperature distribution, I do want you to start from like the heat equation or the fin equation, and then derive that solution from that. And so if it's something like you're solving a differential equation, I do want you to show your work for that. Yeah. So start from the original equation and then solve the differential equation from there.
I see, like including boundary conditions, solving for the
correct
constants and stuff. I see.
Yeah.
I see, because like for part A, like I know like how to do it or where it comes from, like the formula of theta x, but it was just on the notes, just like a temperature, like solving for a temperature distribution in a long rod.
I see.
So I just used that formula, and then I just wrote temperature distribution for a long rod.
I see. Yeah, for that one, I would want you to start from the differential equation, and then and go through and apply the boundary conditions for that, because that's a lot of that's kind of the main thing for those problems.
I see. So like, just to confirm, you're saying for part A, I should start from the beginning?
Yes. Yeah. And I'll be clear on that on the exam as well.
I see.
Yeah.
Well, thank you, Professor.
Yep.
Have a good one.
Thanks, you too.